choked flow, the flow is governed by gamma, not the pressure difference. But if it is not choked, the flow is governed by the pressure difference. In order to find the mass flow rate through valve open area, we have to find the effective valve open area. For that, usually we use two geometric areas, geometric minimum areas. One is valve curtain area, and the other one is valve seat area. And whatever the area that you use, you'll have to use them with the corresponding valve flow coefficient in order to find the effective flow area. Now, if you look at the curtain area, which is what you can see here, is the real valve open area, that is pi d into L, where d is the valve seat diameter and L is the valve lift. The seat area is a fixed value, that is pi over 4 into d squared. So that is the seat area, which does not depend on how much the valve opens. So the coefficient, the flow coefficient, will take care of that part. Accordingly, the valve flow area or the effective valve flow area could be represented as, if the seat area is used, CF into pi over 4 into d squared. So that is the valve seat area into CF. CF is the flow coefficient. And we use curtain area, then CD into pi dl would be the effective area, where CD is the discharge coefficient. Now, if you divide these two areas, CF into pi over 4 into d squared and CD into pi dl, then you will find CD will be equal to CF when d over L equals to 4. So there is a significance of this number 4. We'll get back to that shortly. Now, this diagram shows the valve flow coefficients versus the lift. In fact, L over D ratio is considered here on the x-axis. And in this axis, the ratio of AF over AV, that is the ratio between the coefficients. So the coefficient becomes 1 when L over D ratio is around this one, that is approximately 0.25. So when L over D equals 1 over 4, then the flow coefficient reaches 1. That means the flow will not depend on the valve open area anymore. Accordingly, the valve throat area or the dimensions of the upstream flow path would decide the amount of flow. In this idealistic model, we have not considered any geometric effects like the effect of valve stem and valve seat angle and things like that. Therefore, if you take all these things into account, the maximum value of L over D is about 0.4. So the typical diagram is somewhat related to the real system situation, where you get the maximum value somewhere here. Now, this diagram shows the variation of valve flow coefficient, CF, against L over D ratio. Now you can see CF continue to increase with the increase of L. Yeah, D is constant, diameter of the valve seat. That indicates that valve seat area is a fixed value. So it doesn't depend on the amount of opening of the valve. Therefore, amount of open area will govern by the flow coefficient. So there is a significant variation of L over D, the variation of CF over L over D. On the other hand, if you consider discharge coefficient, where when we use discharge coefficient, we use valve curtain area, and area itself is not a constant or fixed value in the case of seat area, because this L is a variable. As the valve opens, the value of L changes. Accordingly, there is no significant variation of discharge coefficient with the value of D over L. Now, if, for example, for small values of D over L, you can see This is the discharge coefficient, and this is the Reynolds number. When you plot against the Reynolds number, you can see D over L at 0.09 like this, and D over L at 0.2 like this, and D over L at 0.25 like this. So this is the variation at different L over Ds of this CD. Now you can see for small L over D ratios, coefficient CD or the discharge coefficient CD is a function of Reynolds number. So it changes with the Reynolds number. But for medium to high L over D values, the discharge coefficient is independent of the Reynolds number. We'll look at the reasons for that in a very short time. Now, if you look at the real flow pattern through the valves, for very low lifts, you can see the inlet jet, the flow jet, is attached to both the valve and valve seat. You can see here, and it is affected by the viscous shear. So there's an attachment of the flow onto these surfaces. Therefore, it is subjected to viscous shear. And that is indicated here at low valve lifts. So the viscous shear affects the flow and hence the discharge coefficient. So that variation you can see in this plot, which is CD over the Reynolds number. The Reynolds number changes with the flow velocity as well as the viscosity. And in the intermediate lifts, you can see a kind of a separation of this attachment to these walls of the jet. And when you go for a high lifts, then you can see it is completely detached. So as a result of that, the viscous flow effects will not come into play when the L over D ratio is greater than a certain value. So that is reflected in this previous diagram. So when L over D is 0.2 or 0.25, then the discharge coefficient is independent of the Reynolds number. But for small lifts, because the flow is attached to the walls, outflow is attached to the walls, then the viscous shear effect come into play. Accordingly, there is a drop of value of CD with the Reynolds number. Now this shows the discharge coefficient versus L over D for intake valves. You can see there are three segments, A, B, and C, where A represents low lifts, B represents intermediate lifts, and C represents high lifts. And the coefficient is slightly increasing with the increased value of L over D. But again, due to flow separation, it drops. The coefficient drops in the initially with the intermediate lifts, and then as a result of the flow separation, and then continue to increase. And the same thing we can see at high lifts, it will continue to drop because the detachment of the flow from the surfaces. In addition to these flow patterns, it is very much required in internal combustion engines to generate certain special type of flow patterns in the intake system. One such type is the swirl. Swirl means the rotation of incoming air, which enables generating turbulence and mixing air and fuel together. For example, in case of spark ignition engines. Accordingly, this intake port is geometrically modified in such a way that the flow, the swirl flow is enabled. In addition to that, there's another requirement called tumble flow, that is just rotation about an axis perpendicular to the axis of motion. So this is rotation along the axis of rotation, about the axis of rotation, and this one is a rotation around the perpendicular axis to the axis of motion of the pistons. Accordingly, these two flow patterns also affect the valve flow, the flow through the valves to some extent. Now, this diagram shows the mass flow rate through the intake valve. As the valve opens, you can see the mass flow rate increases, and as the valve closes, the flow rate reduces. But more importantly, during valve overlap period, we could experience some intake gases going out of the system through the exhaust valve, so negative flow. And at the same time, as we looked at earlier, usually intake valve is kept open beyond the bottom dead center. Then at low speed and low load conditions, there can be backflow. That is, intake gas come back to the intake manifold again due to increase of pressure inside the cylinder. So there can be some backflow over here as well. So this is a typical a variation of mass flow rate with the intake valve opening. And this is the same thing for exhaust valves under different speeds. You can see. So there's no backflow in this case. But this is the exhaust valve open, this is the exhaust valve closed, and this is how usually. As you see on this diagram, as the exhaust valve opens, the pressure inside the cylinder is much higher than the pressure in the exhaust manifold. Accordingly, the pressure ratio is greater than the critical pressure ratio. Thus, the Mach number is greater than 1 and the flow is sonic. You can see these are experimental data. We can see the mass flow rate does not depend on significantly on the speed of the engine. But after some time, the pressure drops and the Mach number becomes less than 1, so that the normal flow is expected, where you can see it is highly dependent on the speed of operation of the engine. And if you can do the similar analysis, you can find out the flow through the throttle plate also. The throttle plate geometry is given here. The psi is the valve open angle, and D is the diameter of this pin. And we can find the areas geometrically as a function of the diameter of the throttle opening. And I'm not so interested in finding these areas, but what I just want to show is using the same equation that we have derived earlier, by applying the correct pressure values. Stagnation pressure is upstream pressure and PT is the downstream pressure. And we will be able to find the mass flow rate through the throttle plate if you can find the areas and other parameters, as you can see here. If the Mach number equal or more than 1, then the flow through the throttle plate becomes choked, and the critical pressure ratio will be able to work out as before. And the mass flow rate or the critical mass flow rate through the throttle can be worked out this way. And this diagram shows us the variation of airflow rate for various intake manifolds at different speeds and throttle open conditions. So this is wide open throttle, and these are different speeds. And you can see now when the pressure is beyond the critical pressure ratio, that is 1.86, PO over PT is 1.86, and PT over PO will be 1 upon this one, which we earlier looked at, which is 0.54, and which is 5.4. And if the environmental ambient condition is 1 atm, then that pressure value in terms of centimeter mercury, 40.1. So you can see when the manifold pressure is less than the critical pressure, in this case, 40.1, the airflow rate becomes constant for a given throttle angle. Accordingly, airflow rate does not depend on the manifold pressure or the engine speed. under critical flow conditions. Now, in addition to the flow-through valves, there are a couple of other interesting flow phenomena takes place within the internal combustion engines during the intake and exhaust strokes. One such effect is the ram effect. The ram effect is kind of an increase of pressure due to the inertia effects of the gas molecules. Increase of pressure due to inertia of the gas molecules. So this enables gases to flow into the cylinder even after the pistons start moving up from the bottom dead center during the intake, for example. Now, if you can recall, we looked at earlier, intake valve is kept open even after the piston reaches its bottom dead center. And as I said earlier, under low speed conditions, it can be negative because there can be some backflow. That is what we saw in that mass flow diagram as well. But at high speeds, there is an advantage of doing that because as a result of this ram effect or the inertia of the gas molecules coming in, that momentum drives more air into the system. So that is called the ram effect. Usually happens when the piston starts moving up from the bottom dead center at high speeds. And this can occur in both intake and exhaust process. And if you can look at a little bit in detail about this ram effect, and if you can take 2 points, 1 and 2, this is an upstream point with an intake air velocity u, and this is a point on the valve open area, point 2. And if you consider small area in the runner with length dl and area a, and if the pressure difference between one side, pressure difference between two sides of the small area is delta P, then you can use F equals ma to work out the or relate the forces into the acceleration of the flow. So then the force is dP into A, the pressure force, and mass is rho A over dl, that is the volume. And acceleration is obviously du over dt, the first derivative of the velocity. If you assume this runner area is constant for simplified investigation, then the pressure difference between 2 points would be minus rho into integral du over dt across a length of L between this 0.1 and 0.2. So there's a minus sign in front of this because P2 is always less than P1, where point number 2 is a point on the valve open area, that is the downstream of the flow. And if you consider the things on average basis again, if the engine is a 4-stroke engine, we know that du over dt is the acceleration, that is velocity over the time period for one cycle, for example. So if it is a 4-stroke, then it is 1/2 n. N is the speed in revolutions a second. And then the volume flow rate, as we looked at earlier, whatever comes in through the intake system should go into the cylinder. So if the cylinder on average basis going at mean piston speed, and AP is the cross-section area of the cylinder, so this is the volume flow rate. This is the volume flow rate to the system. Rho, if we assume rho is constant, and then this is the volume flow rate coming in. Accordingly, du over dt could be represented using this equation. SP is the mean piston speed, 1/2 n, where n is the speed of the engine in revolutions a second, and AP is the piston area, and IN is the area of the intake system. And if you substitute this into this equation that we have found earlier, then we can obtain a relationship for the pressure difference between 0.1 and 0.2, assuming that this quantity is independent of L. This quantity is independent of L, that is the length from 1 to 2. So we can find a simplified relationship for the pressure difference, which approximately equal to rho SP squared AP over AN into L over simple L over capital L, where capital L is the stroke of the engine and simple L is the runner length between points 1 and 2. So you can obviously see the pressure difference is created due to the speed, and it is a function of density and the speed, square of the speed. So higher the speed, greater the pressure difference. So that is what is meant by the RAM effect. The next one is the tuning. So intake or exhaust tuning is due to something called pulsating flow into and out of the cylinder during the intake and exhaust process. So it's a pressure wave generated within the system, which creates a pulsating flow. So that can be inward and outward flow, and it can sometimes be positive and it can be sometimes negative, depending upon the directions of the pressure flow. And as a result of these pressure waves hitting the going out, for example, from the cylinder and hitting the walls of the intake system, it will reflect back, and that reflection would drag more air into the cylinder. So that is called tuning effect. You can see this variation of pressure against the crank angle in the intake system as well as exhaust system at different speeds. So this is, and you can see at high speeds, the amplitude of these pressure waves are larger. So this is 4,800 revolutions a minute, and this is 1,200 revolutions a minute. So you can see when the speed increases, the pressure waves, amplitude of pressure waves also increases, and accordingly, this could be a positive effect in certain conditions, particularly at high speeds, where these pressure waves hitting the walls of intake system, for example, and reflecting back, drag more air into the cylinder. So this people have done a lot of analysis on this tuning effects and have found that the frequency of oscillation also could be related to certain geometric parameters of the intake system. For example, frequency of oscillation would be equal to C over 2 pi, where C is the speed of sound, square root of A2. A2 is the area of this cross-section area of the air duct, and L2 into V2. V is the volume, L is the intake pipe length, and so forth. And in a simplified and approximated analysis, it is quite reasonable to assume that this V2 is half of the displaced volume of the engine. Now you can see here this variation of volumetric efficiency against the speed with different values of L, that is the runner length. And you can see the effect of tuning in this case, where at high speeds in particular, when the value of L is smaller, then the volumetric efficiency is higher. So that is due to effect of tuning. And this diagram shows the valve flow through exhaust valves. And this is the discharge coefficient against L over D ratio. And usually exhaust flow operates at a pressure ratios from 1 to 5, mostly higher than the case of intake system. Accordingly, most of the time during the exhaust, the flow is critical. So the flow pattern is at high lifts. You can see the separation of the flow from the walls. At low lifts, the flow is attached. Accordingly, you can see at low lifts, CD value is larger as well as almost constant. But due to the separation, when the value of lift is high, then the discharge coefficient starts dropping down. Let's look at gas exhaust blowdown little in detail. I introduced this term earlier as well. The gas blowdown takes place when the exhaust valve opens, when the piston comes down during the expansion stroke before it reaches the bottom dead center. So as you can see on the bottom diagram, so the exhaust valve opens here, and accordingly some exhaust gases, the exhaust gases in fact start going out of the system. And this process would improve the engine efficiency and reduce emissions and enhance the overall performance by efficiently sending exhaust gases out of the system. Now, to look at what happens during this exhaust gas blowdown in a simplified way, let's consider control volume in the exhaust the process with the instantaneous mass mt, pressure pt, time temperature t, tt, and E is the exiting condition, and effective area of the valve flow is AF. So the exhaust gas mass flow rate we can write down in this out of this control volume is dm over dt, and that is going out of the system. Therefore, it is minus me dot. And then if there is no work or heat transfer during this process, for the simplified analysis, the rate of change of energy will be equal to rate of change of enthalpy of the exhaust system. And if it is ideal gas with constant specific heat, then at any given time, the energy in the control volume would be mcv t. Energy is cvdt, so in any time, we could say mcv t. And if you take the first derivative of this, then this will become dE over dt, so that we could equate this to this accordingly. So we know that the enthalpy is Cpt. Accordingly, the energy equation would become first derivative of the energy equation, Cv assumed to be a constant. Therefore, first derivative of this mt multiplication, this will be equal to the enthalpy of the system as indicated by this one. The first derivative of this one will be the same as this one. So, so that will be equate to this, and accordingly, a slight rearrangement of these terms would give you mcv dt, so that is this quantity, equal to minus this one, so that is minus me dot rt. So Cp minus Cv is R. It's an ideal gas property. And now this gas blowdown takes place when the cylinder pressure is quite high before it reaches the bottom dead center. Therefore, the flow is usually choked. Flow is usually choked because the pressure ratio is greater than 1.86. Accordingly, we can, to find the mass flow rate, or m dot E, we could consider the flow through orifices under choked conditions. So this is something that we looked at earlier, where K is a function of specific heat ratio. So the same equation that we looked at earlier. Then we can substitute this one into the energy equation instead of this me dot, so that equation becomes this one, where this me dot is replaced by this one. And with a little bit of simplification, considering the properties of ideal gas, relationships of ideal gas, we could get a relationship for dt over dt, that is the rate of change of temperature as a function of some parameters, as you can see here. And further simplifications or integration of this equation with certain initial conditions give us time required to expel gases. So the temperature relationship, this equation becomes this through integration, where C is this parameter. And then if you replace these temperatures with pressure, pressure ratio, assuming the isentropic flow down. So we can replace these temperatures with pressures, and the time for blow down could be calculated accordingly. With this background, if you look at the volumetric efficiency under these different flow situations, now ideally we would like to have the volumetric efficiency 100%, but we will never be able to achieve this 100% ideal volumetric efficiency in practical engines. So one reason is initially due to quasi-static effects, there is a drop of volumetric efficiency. And then comes the intake system flow friction into play as a dynamic effect. And that will also drops the volumetric efficiency, especially at high speed conditions. And then the flow should pass through these small orifices like valves, etc. And then there is a resistance to flow at those points, and that will further push the volumetric efficiency down, particularly quite high at the high speeds and small in the low speeds. And then comes to the heat transfer within the system. Heat transfer would increase the temperature of the intake mixture, and accordingly the density would be reduced. As a result of that, there will be a drop of volumetric efficiency. Now, the drop of volumetric efficiency at low speeds is more compared to the drop in the high speeds, because at high speeds, time available for heat transfer is less. And then comes the timing effects at low speeds. Due to the early inlet valve open, there will be some backflow taking place. So that backflow would drop the volumetric efficiency at low speed conditions. But again, at the high speed conditions, due to ram effects, this volumetric efficiency would be increased. So accordingly, the valve timing would have a positive effect at high speeds and negative effect at low speeds. And then comes the choking at high speeds at different positions at valves as well as at the throttle in spark ignition engines. So there can be further drop of volumetric efficiency due to choking. And then when the mixture come into the cylinder, then within the cylinder also there can be certain degree of heat transfer, which would heat up the gases and accordingly drops the density. That will also reduce the volumetric efficiency. And then finally, as we know, the exhaust and intake valve tuning enhances the flow, accordingly the volumetric efficiency. So the volumetric efficiency would be increased. Again, the tuning effects are more significant in the mid-speed range. So the volumetric efficiency in general, the variation of volumetric efficiency with the engine speed would look like this. And in general, the diesel engines will have a greater volumetric efficiency or higher volumetric efficiency than the spark ignition engines due to obvious reasons. That is, the volumetric efficiency in spark ignition engines is lower because of these throttle losses. There is no throttle losses in diesel engines. And you can see there is a double peak in the diesel, particularly with the diesel engines. That is due to the tuning effects. The tuning effects, there you can see double peaks in the curve of volumetric efficiency with the speed, particularly for diesel engines. So the volumetric efficiency is a key parameter in the intake system design, and a volumetric efficiency is affected by the fuel ratio, fuel vaporization, mixture temperature, the throttle position, ratio of inlet to exhaust manifold pressures, the compression ratio, engine speed, and the intake exhaust port designs, as well as the valve geometries and things like that. Volumetric efficiency is affected by many parameters, and certain parameters are engine intake system design parameters, which could be taken into consideration when you design an intake system.